Right Academy. Learn it, teach it, remember it, backtracking. By the end of this, you won't just use it. You'll feel its shape before you ever read the code. Forget the word for a moment, you already know how to do this. You're standing at the entrance of a hedge maze, and at the first fork you pick a direction. You walk it fork after fork, going deeper and deeper. And then you hit a wall, a flat dead end, with nowhere left to go. Here is the only rule that really matters. You tie a string at the entrance and you unspool it as you walk. When you dead end, you don't start over, you reel the string back to the last fork you haven't fully tried. That fork still has a road you skipped. So you take it and the string becomes your memory of the way back. 3 simple things happened in that little story. At every fork, you make a choice. You explore wherever that choice leads. And when it dead ends, you unchoose and back up. Choose, explore, unchoose. That one rhythm solves a surprising range of problems. Now redraw that maze so we can reason about it cleanly. Every situation becomes a dot and every choice an arrow to the next one. Put them together and you get a tree rooted at the entrance. Each path down to a leaf is one full attempt, and the dots in between are partial ones. Backtracking is really just walking this tree. You go as deep as you can down one branch. When you can't go deeper, you step back up one edge and take the next option. Always deeper before wider, that is a depth-first search of the partial solutions. Here is the heartbeat of every backtracking solution, 3 steps in a fixed order. Choose, commit to an option, and push it onto the path. Explore, recurse, and solve the rest with that choice in place. Unchoose when it returns, undo it and pop it back off. And at the very top, one check, are we done? And if so, we record it. Why must you undo it all? The path is shared across every branch, so choose A, dive and forget to remove it, and branch B still carries A. Unchoosing resets the world to a clean fork, so B starts fresh. And when the whole search ends, the path is empty again, every push matched by a pop, so the actual skeleton is tiny. If the partial answer is already complete, record it and return. Otherwise, for each available option, you choose it, recurse, then unchoose it. That choose and unchoose are a matched pair, like opening and closing a bracket. Let's make it concrete on the cleanest problem there is. List every ordering of 3 items, A, B, and C, and there are exactly 6 of them. We carry a path so far, and a set of items still available to use. Walk the tree from the top, always diving on the first available item. Choose A, then B, and only C is left, so the path is full. That is a leaf, so record A, B, C. Unchoose back, and from A take C instead, giving A, C, B. Unchoose to empty, start with B, and the same dance gives B, A, C, and B, C, A. Then C gives C, A, B, and C, B, A. 6 leaves, 6 orderings, and we were never clever, the tree enumerated them all. Watch one detail you will reuse forever. A is the first letter of ABC, and later it is the second letter of BAC because the unchoose put it back into available. Forget that unchoose, and A is consumed after its first use, and the rest comes out as garbage. Permutations are one shape, subsets are the other. For the set 1, 2, 3, list every selection, not the order but simply in or out. There are 8 of them, from the empty set to the whole thing. The fork is different now. At each item you either take it or skip it. Take it and the item joins your set. Skip it and you move on without it. March through item 1, 2, and 3 including all 3 for the full set. Then back up and try excluding all the way down to the empty set. 8 leaves, 8 subsets, same frame but a different fork. Permutations forked on which remaining item, subsets forked on in or out. The choose, explore, unchoose skeleton never changed, only the menu did. And notice where the answers live. For subsets, every node is a real answer. For permutations, only the full-length leaves. So far, we visited every single leaf. And for 3 items, that is fine. But the tree grows ferociously, and 10 items already number in the millions. 20 items is more than the second since the universe began. A search that visits every leaf will simply never finish on real inputs. Here is the second half, and it is gloriously simple. The moment a partial answer cannot possibly lead to a valid one, you stop and back up. That is pruning. You lop off a whole branch, and everything below it goes too. Cut near the top, and you throw away an enormous subtree without visiting a single leaf. The trick is recognizing hopeless as early as you possibly can. Check only at the leaf, and you have already built a whole doomed candidate, that is brute force in a costume. Check at every choose, and you refuse a bad path while it is still short. The earlier the proof, the bigger the subtree you save. Now the classic problem backtracking was invented for. Place queens on a board so none attack each other along any row, column, or diagonal. A queen attacks its whole row so no row can hold 2. That turns it into 1 choice per row, namely which column. And now the prune. Place a queen and it threatens its column and both diagonals. Before we recurse on a square in the next row, we ask one thing: is it attacked? If yes, the branch is doomed, so we refuse it and never recurse. Watch it bite square by square. Row 1, column 1. Down to row 2, columns 1 and 2 are attacked, but column 3 is safe. Down to row 3, every column is attacked, a dead end, so back up. Try column 4 in row 2 instead, and place row 3 at column 2. But now row 4 has nowhere to go, another dead end. The whole subtree under column 1 is exhausted. Start row 1 at column 2 instead, and this branch reaches a full safe board, so record it. Sit with what pruning just bought us. 4 rows and 4 columns means 256 full boards to build and check. With pruning, we built only a handful. The tree was always there, pruning simply refused to walk the dead parts of it. Why should you trust this? It is complete. The loop offers every option that is not provably doomed, so no valid leaf is ever cut off. And it is clean. The unchoose means each leaf is reached by exactly 1 path. Complete and clean, that is the whole correctness argument. So how slow is it, really? The runtime is just the number of nodes the search visits. The unpruned tree is enormous, factorial for orderings, doubling for subsets. Pruning changes the constant, not the worst case, so it is still exponential. What it buys you is a feasible search of an exponential space, and better pruning is the whole game. The memory cost, by contrast, is small and lovely. At any instant, you hold exactly 1 path, from the root to where you are. Its length is just the depth of the tree, the size of a single candidate. You explore an astronomically large space while only ever holding 1 slim path. 4 mistakes break most backtrackers. 1. Forgetting to unchoose, the cardinal sin. 2. A wrong or missing base case. 3. Pruning too late or not at all. 4. Duplicates when the input repeats. The cure for all 4. Trace a tiny input by hand and watch where the tree surprises you. How do you spot one of these in the wild? Just ask 4 things. 1. Are you building something from a sequence of choices? 2. Do you want all valid configurations or one under tight constraints? 3. Can you make 1 choice now, leaving a smaller version of the same problem? 4. Do the constraints let you reject a partial answer early? 4 yeses, and it is backtracking. You master this by drawing the tree out loud on a ladder of problems. Subsets, then permutations, then combination sum, then the queens, then a full puzzle like Sudoku. Each time, name the choice at each level before you write a single line. So here is the one idea to carry out the door. Backtracking is depth-first search over a tree of partial solutions. Choose, explore, unchoose, and prune the moment a branch is hopeless. A complete search, made feasible by refusing to walk what was never going to work. Want to keep learning? Come find us at academy.rudewrite.com.